In the last video, Planck created the blackbody radiation formula. Now, Planck had to develop a physical model that should explain the different fire colors that appear when we burn a block of wood. From electromagnetic theory, Planck knew that oscillating electric charges would emit light. So, he assumes each oscillator oscillates with a different frequency, emitting only a single color. So, he fixed various oscillators that emit different light colors. He set multiple oscillators that emit different light colors on the blackbody's wall. If the walls of the blackbody are heated, it provides energy to the oscillators to set in motion. When the oscillators are in motion, it emits light. So Planck assumed at a specific temperature, more number of particular color oscillators are active. For instance, at around 800 degrees Celsius, more red oscillators are active. But the problem is that at 800 degrees Celsius, the predominant color is red, but all other colors also appear. So for this model, Planck needs to get the right mixture of color inside the black body at a particular temperature. Unfortunately, Planck found it hard to derive its equation using the accepted physics during that time. He turned to Ludwig Boltzmann. Ludwig Boltzmann followed James Clerk Maxwell and used statistics to interpret the second law of thermodynamics and entropy. So, what is second law of thermodynamics and entropy? Entropy means the measure of disorder. If something is in order, its entropy is less. But if something is in more disorder, then the entropy is large. The second law of thermodynamics means heat always transfers from hot to cold bodies. That implies entropy always increases. But according to Boltzmann, a new pack of playing cards is less disordered, but well shuffled cards are more disordered. So, for example, if we shuffle the cards, they will always be in disorder. But according to Boltzmann, if we mix enough, all the cards will be in order again. Thus, the entropy can also decrease. The second law of thermodynamics says heat always transfers from hot to cold bodies. But according to statistics, heat means the movement of particles. The molecules move faster in hot bodies compared to the cold bodies. Since each molecule collides with the other, these molecules have a wide range of velocities. Even in cold bodies, some molecules move faster due to collision. If we put hot gases into one box and cold gases in the other box and connect by making small holes between them, the fastest molecule in the cold gas moves to the hot box. Thus, heat transfers from cold to hot bodies. That implies entropy can also decrease. But Planck believes entropy is absolute. It always increases. That is, the heat always transfers from hot to cold bodies. But Planck had to follow Boltzmann to explain the blackbody spectrum so that a wide range of oscillators would be active at a particular temperature. Thus, light behaves like gas particles. So, Planck had to accept that light would act like particles. But Planck and other physicists in those days always believed light is continuous waves, as explained by Maxwell's electromagnetic theory. However, Einstein thought electromagnetic waves were not wave-like but chopped into little bits of light quanta. Einstein imagined an empty black body. He filled it with gas particles and electrons. The atoms of the wall of the black body contained other electrons. As the black body is heated, they oscillate with a broad frequency range. They emit radiation. Soon, the interior of the black body is steamed with speeding gas particles and electrons and radiation emitted by oscillating electrons. After a while, everything inside is at the same temperature. The energy of the black body is conserved. Now, Einstein used Wein's law and Boltzmann's idea to analyze how the entropy of blackbody radiation changes when we reduce the volume. He found a formula similar to the Joule expansion of a perfect gas. Blackbody radiation behaved as if it was made up of individual pot-like bits of energy. Planck only quantized the emission and absorption of electromagnetic radiation. Einstein found light itself is quantized. Now, Einstein wants to check that considering light as a particle could solve any unsolved problems. He felt three phenomena that a classical electromagnetic theory cannot explain: photoelectric effect, Stokes shift, photoionization. In 1887, Heinrich Hertz was trying to prove Maxwell's electromagnetic theory that light is a wave. In that experiment, two metal plates were connected by a metal rod with a metallic sphere at the end. When the induction coil gives a oscillating high voltage supply, we can see the spark between the air gap now. If the light is an electromagnetic wave, it propagates in the air and produces a spark in the detector. So that proves light is a wave. In the same experiment, he noticed the spark between two spheres becomes brighter when one of them was illuminated by UV light. Later, it was found that a spark was due to emission of electrons. Einstein's solution was simple. If the light is quanta, if we send yellow light, it has low energy, so it does not have energy to remove electrons from the surface. But if we send ultraviolet light, which has high energy, can remove electrons from the surface. Photoionization. Let's take a chamber supplied with a gas particles and insert two electrodes connected to an electric circuit. When we shine UV light, the gas particle absorbs UV light to cause electron to leave and create an positive ion. Then the current of negative and positive ions flows. We can explain this if we consider light as a particle. Stokes shift. In the mid 19th century, G.G. Stokes studied fluorescence properties and investigated how the properties of fluorescence light differed from incident light. For instance, if we send a green light through fluorescence, it absorbs green light and emits red light. So there is a shift in the spectrum due to an energy reduction. This energy reduction is Stokes shift. Considering light as a wave can explain diffraction, refraction, reflection, and interference. But considering light as a particle can explain blackbody radiation, photoelectric effect, Stokes shift, and ionization. Now, whether the light is a wave or a particle, how was this problem solved? And the other discoveries during that time are all we will see in the later videos. Thank you. See you in the next video.